Optimization is taking a real-life situation and finding the extrema. We either want to maximize something or we want to minimize something. So we know the first derivative test gives us extrema. In these problems, though, if I ask you to maximize something, you can assume that the critical point that you find is a maximum. I'm not going to ask you to find the max and then give you a function that only has a minimum. So you don't have to actually do the first derivative test, but you do have to take the first derivative in order to get the critical points, which are going to be our extrema. So in these problems, you're going to have one equation that you write, and that's the equation that you want to optimize. So we're going to take the derivative of it. You're going to have another equation that helps you write the first equation in terms of only one variable. So here's an easy one. Find two non-negative numbers with a sum of 20 that give the greatest product. Non-negative, that means it could be 0 or a positive number. They have a sum of 20. So let's write that. As an equation. I'm just going to pick x and y for my two numbers. When I add them together, their sum, means add, is 20, and they give the greatest product. Product means multiply. So let's let P stand for product. So my equation P equals x times y is the one that we are trying to optimize. I'm looking for the greatest product. I'm trying to get a maximum product. But if I'm going to take the derivative of this, I want it in terms of one variable. I want to either ddx it or ddy it. We're used to working with x, so I'm going to put everything in terms of x. So that means over here, I'm going to solve for y so that I can rewrite my product equation just in terms of x, and I'll distribute that x, and I get 20x minus x squared. Now, if we think about that graph, that's a parabola opens down. So it's going to have a maximum at the vertex, right? All right, so in order to find that point, we need to take the derivative. So the derivative of 20x is 20. Derivative of negative x squared is negative 2x. And then we know we have to set that equal to 0. I'll add 2x to both sides, and I get 2x equals 20. And if I divide both sides by 2, we get x equals 10. Again, I don't have to do the first derivative test on this to make sure it's a max because I'm not trying to trick you. If I ask you to maximize a problem, the critical point you find is going to be the max. So that means my first number is 10. I need to plug that in to this equation to get y, or right there. That one's already solved for y. So I get y equals 20 minus 10. It's also 10. Okay, so if x and y are both 10, when I add them together, I get 20. That's our first constraint. And if I multiply them to get the product, I get 100, and that would be the maximum. So actually, if this is a parabola that opens down, its vertex occurs at 10, 10. Of all rectangles with an area of 12, which has the minimum perimeter? Well, let's draw a rectangle here. And rectangles, the area is length times width, right?
Yeah.
So let's make that length and width. So I would say area is length times width. And the perimeter is if I walk around the entire outside of this thing and add up all the side lengths. So my perimeter is going to be 2L plus 2W. That is the equation that we are trying to minimize. That's the one I'm going to take a derivative of. My area was given, it's 12, so we need to solve for one of those variables. And since it's length and width, I don't really have a preference. Let's solve for W. So I'll divide both sides by L. We get W equals 12 over L. So I'm going to plug that into my perimeter equation.
It doesn't matter which one you try to solve for, whether it's the
Nope.
L or W. Just
No, because I'm going to end up finding both. Doesn't matter, L or W. Eventually I'm going to end up with a number for L and a number for W. All right, let's rewrite this is 2L plus 24 over L. All right, so we want to take a derivative of this because we're trying to optimize it. So P prime is going to be 2. Now, this is 24L to the negative 1, right? That's what 24 over L is. So a negative 1 comes out front, and we get L to the negative 2, or 24 over L squared. So we set that equal to 0 to find our critical points. And I get 2 equals 24 over L squared. I added the 24 over L squared to both sides, basically. Multiply both sides by L squared, and I get 2L squared equals 24. So I'm going to bring this over here to the right. L squared is going to be 24 divided by 2. That's 12. If I take a square root, I'm going to get plus or minus the square root of 12. Does it make sense to get a negative here? No, because it's a length. So we're only worried about the positive square root of 12. And 12 is 4 times 3, so I can simplify this and make it 2 root 3. Okay, so I have my length. I need my width. I need to plug this in here to get my width. So W equals 12 divided by 2 root 3. Well, 12 over 2 is going to go to 6. I have 6 over root 3. And if we rationalize that, we're going to get 6 root 3 over 3. And 6 over 3 goes to 2. So we get 2 root 3. So my L and my W are both the same. That was true in the last problem as well.
But it said it's a rectangle.
Yeah, that's what I was thinking.
A square is a subset of a rectangle.
Yeah.
It's a special case of a rectangle.
But also, like,
Find the length and width of a rectangle with a perimeter of 26 units and maximum area. So last time we were minimizing perimeter and we were given area. This time we're given perimeter and we're maximizing area. So let's draw a rectangle and we'll go with length and width again. Perimeter is 2 times length plus 2 times width, and we are given that that is 26. My area is what I want to maximize, is length times width. So we need to solve for a variable, and I'm going to go with let's solve for L. So I'm going to subtract 2W from both sides. I get 26 minus 2W equals 2L. Divide everything by 2, and we get L equals, now 26 divided by 2 is 13, and 2W divided by 2 is just W. So we get 13 minus W. So if I plug that in to my area equation, we get 13 minus W times W, which is 13W minus W squared. So that's my area. We want to maximize it, so we've got to take a derivative. So A prime is going to be 13 minus 2W. We set that equal to 0 to find our critical points. So if I add 2W to both sides, I get 2W equals 13, and W equals 13 over 2. So L is 13 minus 13 over 2. So 13 is really 26 over 2 minus 13 over 2 gives us 13 over 2. I got the same answer for the length and the width. So it turns out a square is what maximized my area.
So it's all in this. Yeah.
A rancher has 400 feet of fence to make a rectangular pen with one side formed by the side of a barn. So what's this going to look like? I have a side of a barn here, so it is providing one side of my fence to make the pen. And for my fencing, I'm coming off the barn there. And so if we call this Y and this Y and this X, then that has to add up to be 400 feet of fence. What is the maximum area of the pen? So what's the area of this going to be? It's X times Y, right? All right, so the equation we have to optimize is X times Y. And I have to solve this first equation for a variable. It's going to be easiest to solve for X, right? So we're just going to subtract 2y from both sides, and we're going to get x equals 400 minus 2y. So our area becomes 400 minus 2y times y. Let's distribute that y. We get 400y minus 2y squared. And we need to take a derivative. So my derivative is going to be 400 minus 4y. And if we set that equal to 0, I can add 4y to both sides. And we're going to get y equals 100. So to find x, we need to go back to this equation here. X equals 400 minus 2 times y, which is 100. So x equals 200, y equals 100. We'll maximize the area of this pen, given the constraint that I only have 400 feet of fence to work with. Now let's change the situation a little bit. My rancher wants to separate the pen into 3 rectangular regions. What dimensions will maximize the enclosed area? What is the area of each rectangular region? So what does this look like? So I got my side of my barn. And now I'm going to take my rectangle and separate it into 3 regions. So now I have y there, and there, and there, and there. And we'll make that whole thing x. So my area of the entire thing is x times y. And that's what we're trying to maximize, is the entire enclosed area. And now we have 400 feet of fence, but it has to add up to be 4y plus x. And if we solve that for x, we're going to get x equals 400 minus 4y. So my area equation becomes 400 minus 4y times y. Distribute that y, I get 400y minus 4y squared. And now we take a derivative. Derivative of 400y is 400. Derivative of negative 4y squared is negative 8y. Set it equal to 0 to find the critical points. If I add 8y to both sides, I get 8y equals 400, and y equals 50 feet of fence. So then I'm going to get x from right there. So x equals 400 minus 4 times 50. So x equals 200 feet.
We already knew that.
That didn't have to come out to be the same.
Well, if you only have one axis,
Just ask me to agree with it.
because you couldn't change the rectangle previous.
Oh, I could. So we found the dimensions that maximize the total area, but I'm also being asked, what is the area of each rectangular region? Now, all of them are the same, correct? So if I find the total area, I can just divide it by 3 and I'll have the area of each region. Does it make sense? So my total area is x times y, so it's 200 times 50, which is 10,000 square feet. Remember, we were told that our fence was 400 feet, so I know my units are feet times feet gives me feet squared. That's my total area. The area of each pin is that divided by 3. And so I'm going to get 3,333 feet with a 0.3 repeating decimal, but we'll just round to the nearest one here.